Causal discovery in linear models is a challenging task, especially when unobserved variables and measurement error are present. This paper addresses the problem of identifying a linear latent variable structural equation model with measurement error, LVSEMME, from observational data. The model includes 4 types of variables: directly observed variables, variables not directly observed but measured with error, the corresponding measurements, and variables that are neither observed nor measured. The authors characterize the extent of identifiability of the linear LVSEMME under 2 versions of faithfulness assumptions. They propose a notion of observational equivalence and provide a graphical characterization of the models that are equivalent. A recovery algorithm is presented that can return models equivalent to the ground truth. The paper discusses the problem of identifying a linear latent variable structural equation model with measurement error from observational data. This model is characterized by 2 sets of variables, v and x, where v can be arranged in a causal order and each variable in v is generated as a linear combination of its direct parents plus an exogenous noise term. The variables in v are further partitioned into 3 sets: y, observed variables; z, measured variables; and h, unobserved variables. Each variable in x is a noisy measurement of one corresponding variable in z plus an exogenous noise term, known as measurement error. The authors introduce 2 restrictions on the model for the sake of model identifiability based on observational data. Firstly, they assume that the exogenous noise term for any m-leaf variable is not distinguishable from its measurement error. Secondly, they assume that variables in H are all root variables and confounders. The matrix form of the canonical LVSEMME is provided, which includes equations for unobserved variables, observed variables, and measurements. The authors also define the causal diagram of a linear LVSEMME as a directed graph where nodes represent all variables in V union X, and there is a directed edge from W1 to W2 if and only if W1 element of PA, W2. An example of a causal diagram is given, including unobserved variable H, observed variable Y3, measured variables Z1 and Z2, and their corresponding measurements X1 and X2. The paper aims to provide a recovery algorithm that could return all models in the AOG and DOG equivalence classes, where AOG stands for all other graphs, and DOG stands for direct ordered grouping. The authors also discuss the extent of identifiability under 2 versions of faithfulness assumptions and provide preliminary results that were presented in a previous work. In this research paper, the authors delve into the identification problem for linear latent variable structural equation models with measurement errors, LVSEMME, using observational data. They first considered 2 special submodels: the linear structural equation model with measurement errors, SEMME, and the linear latent variable structural equation model, LVSEM. The authors then extend their analysis to the general form of LVSEMME, which includes both unobserved variables and measured variables. To achieve identification, the authors propose 2 assumptions: the separability assumption and the faithfulness assumption. The separability assumption states that the mixing matrix, which transforms independent exogenous noise terms to observed variables, can be recovered from observations of x, y, up to permutation and scaling of its columns. This assumption holds in settings where all exogenous noises are non-Gaussian or when the noise terms are piecewise constant functionals satisfying certain conditions. However, it is violated when all exogenous noise terms have Gaussian distributions. The faithfulness assumption comes in 2 versions: conventional faithfulness and LVSEMME faithfulness. Conventional faithfulness assumes that the total causal effect of any variable on its descendants is non-zero. LVSEMME faithfulness is a stronger assumption that requires the rank of a submatrix of the mixing matrix to be equal to the size of the minimal bottleneck from a set of variables J to a set of variables K. The authors note that both faithfulness assumptions are violated with probability 0 if all model coefficients are drawn randomly and independently from continuous distributions. However, in practice, due to sample size limitations, an approximate cancellation may be perceived as an actual cancellation, making conventional faithfulness a preferred assumption. The authors also present a graphical characterization of equivalence under conventional faithfulness, called ancestral ordered grouping, AOG, equivalence. AOG is a partition of the variables into distinct sets, where each cogent variable is assigned to a distinct group, and M-leaf variables or unobserved variables are assigned to groups based on their parental relationships. The AOG equivalence class is a set of models with the same mixing matrix, up to permutation and scaling, and same ancestral ordered groups. In the context of structural equation models with measurement errors, SEMME, and latent variable structural equation models, LVSEM, the authors investigate the identifiability of these models up to their ancestral ordered group, AOG, equivalence class, and direct ordered grouping, DOG, equivalence class. For SEMME, each ancestral ordered group has at most one cogent variable, and the induced structure on each group is a star graph. Similarly, for LVSEM, each group has exactly one cogent variable, and the rest are unobserved variables that are parents of this node. By fixing the center of the ancestral ordered groups for SEMME and the exogenous noise term for LVSEM, the authors show that the models are uniquely identified. They introduce the concept of direct ordered grouping, DOG, equivalence, a refined partition compared to AOG, where each cogent variable is assigned to a distinct group, and M-leaf variables or unobserved variables are assigned to the same ordered group as their parents or children if certain conditions are satisfied. The authors prove that models in the same DOG equivalence class have the same edges across groups and the same in-labeled graph structure for SEMME, and the same graph structure for LVSEM. They conclude that the DOG equivalence class provides a more distinctive characterization of causal relations among variables compared to the AOG equivalence class. In the context of linear latent variable structural equation models with measurement error, LVSEMME, the authors present an approach to identify the model up to its AOG or DOG equivalence class, leveraging information about measured and observed variables. They introduce the concept of minimality, which asserts that the ground truth model has fewer unobserved variables than any other models with the same mixing matrix and observability indicator. The authors present the main identification result for the LVSEMME model, providing results under assumptions 1 and 3, and introduce recovery algorithms for the introduced model. The paper presents two algorithms for recovering the ancestral ordered group, AOG, and model parameters in the AOG and directed ordered group, DOG, equivalence class of a linear latent variable structural equation model with measurement error, LVSEMME. Algorithm 1 identifies the AOG from the mixing matrix W** operator by iteratively selecting rows and columns with the fewest number of non-zero entries, assigning them to separate groups based on their support, and checking whether any row corresponds to a cogent variable. The algorithm continues until all variables and noises are assigned to ordered groups. Algorithm 2 recovers the models in the AOG and DOG equivalence class by first recovering the AOG using algorithm 1, then enumerating all possible choices of centers and noises for each group. For groups with only M-leaf variables or unobserved variables, there is only one choice. For groups including cogent variables, the algorithm considers all possible selections of centers and noises, calculates the model parameters B, C, D based on W** operator and the selected row and col, and thus obtains all models in the AOG equivalence class. Both algorithms have a computational complexity of O, PCMN, and a space complexity of O, Mn, where M and N are the dimensions of the mixing matrix W** operator. The authors leverage proposition 6 to recover models in the DOG equivalence class, which is defined as the set of models with the fewest edges. They show that any model that belongs to the same AOG equivalence class but does not belong to the same DOG equivalence class has strictly more edges than any member in the DOG equivalence class. The paper concludes that the methodology can learn the model up to the AOG and DOG equivalence classes under certain assumptions, but notes that the accuracy of the provided estimate of the mixing matrix and the linearity assumption are limitations that require further research. This section reviews linear non-Gaussian causal models, focusing on identification and estimation in the presence of latent variables and measurement error. The authors discuss key concepts, such as the linear non-Gaussian acyclic model, LINGM, and highlight the importance of considering latent variables and measurement error in causal modeling. Various approaches for dealing with these challenges are reviewed, including anchored discrete factor analysis and greedy search algorithms. The authors emphasize the role of structural identifiability in determining whether a given model can be uniquely identified from observational data. Conditions under which linear non-Gaussian models are identifiable are discussed, including non-Gaussianity and heterogeneity in the data. Recent advances in estimating causal effects using linear non-Gaussian models with hidden variables and new algorithms for learning these models in the presence of latent variables are also covered. The proof of Proposition 2 is presented in two parts: sufficiency and necessity. The sufficiency part demonstrates that if an unobserved variable has an M-leaf child satisfying the condition described in Proposition 2, then the model is not minimal. The necessity part shows that if the model is not minimal, then there exists an alternative model with fewer unobserved variables that has the same mixing matrix and satisfies conventional faithfulness. Equations 5, 8 describe the structural equations for the variables in the original and alternative models, demonstrating how the alternative model is constructed. The proof involves partitioning variables into groups based on their row support in the mixing matrix and enumerating all models in the ancestral ordered group, AOG, and directed ordered group, DOG, equivalence classes. The structural equations for the variables in the alternative model are derived, showing that the alternative model is acyclic and satisfies conventional faithfulness. The paper examines the structural equations of variables in models M and M, highlighting the differences between the two. In M, the center of a group is denoted as V with exogenous noise NVI, while in M, the center and corresponding exogenous noise are ZJ and NHL, respectively. The structural equations for V, ZJ, and other children of V and HL are provided, illustrating the changes in parent-child relationships among variables in M, compared to M. The paper proves the identification result under conventional faithfulness, showing that the extent of identifiability of an LVSEMME under conventional faithfulness is the AOG equivalence class. This involves proving that for the ground truth model M, any other model M, in the AOG equivalence class of M, and any model M, that has the same mixing matrix but does not belong to the AOG equivalence class of M, satisfies conventional faithfulness, is consistent with any causal order among the ancestral ordered groups that is consistent with M, and M, violates conventional faithfulness. The authors prove that for each cogent variable V, the ancestral ordered group of V includes its M-leaf child ZJ if V is measured and all other parents of ZJ are also ancestors of V, and unobserved parent H if all other children of H are also descendants of V. They also define sup, G, and sup, A, and prove that for two different ancestral ordered groups GI and GJ, the existence of a causal path, sup, GI, subset of sup, GJ, and sup, NGJ, subset of sup, NGI, are equivalent conditions. The authors further prove that given M, a causal order among the groups is consistent with the causal order among the variables if and only if the set relations in the mixing matrix hold. They also show that if M does not belong to the AOG equivalence class of M, then M is not minimal, and that M cannot have more cogent variables than M. The cogent variables in M are denoted as P, and it is shown that no two variables in P belong to the same ancestral ordered group of M, and the exogenous noises of variables in P and M include the exogenous noise of at most one variable in each group. The paper addresses the identifiability of a linear, non-Gaussian, acyclic model, LVSEMME, under LVSEMME faithfulness, aiming to demonstrate that the extent of identifiability is the DOG equivalence class. The authors provide a two-part proof to achieve this. First, they show that any model M, in the DOG equivalence class of the ground truth model M does not add or remove edges compared to M and satisfies LVSEMME faithfulness, making M indistinguishable from M. Second, they demonstrate that any model M, in the AOG equivalence class of M but not in the DOG equivalence class adds at least one extra edge compared to M, does not remove any edge, and violates LVSEMME faithfulness, making M distinguishable from M. The authors then provide detailed proofs for these claims, focusing on models within the same dog equivalence class and models outside the dog equivalence class but within the AOG equivalence class. They violate assumption 3 if an edge is cancelled in M, which is demonstrated through 3 cases. The proof of 2c establishes that M has the same in-labeled graph structure as M by constructing mappings sigma M and sigma n between variables in Z union Y and VC union H, respectively. The model parameters in M and M are related through an invertible mapping, ensuring that if M satisfies assumption 3 with probability 1, then M also satisfies assumption 3 with probability 1. The proof of 2d shows that if M differs from M only in one choice of centers, then there will be at least one edge added to M. The proof of 2e establishes that if any edge is removed in M, then M violates assumption 3. The results imply that if the ground truth model satisfies assumption 3, then the probability that models in the dog equivalence class all satisfy assumption 3 is also 1. The analysis delves into the implications of adding an edge to a model, specifically in the context of ancestral ordered groups, AOGs, and the relationships between variables. The discussion centers around the conditions under which a model, denoted as M, violates assumption 3, which pertains to the existence of a minimal bottleneck in the model. The authors consider various cases based on the type of variable, V, that the added edge connects to, including V being a center node, ZJQ, a non-center node, VKQ, or a latent confounder, VLQ. For each case, the analysis involves defining sets J and K, which represent the variables in M that correspond to the exogenous noise of variables in the ancestral ordered group and the parents of V, respectively. The key finding is that in all cases, the addition of the edge leads to a violation of assumption 3, as the minimal bottleneck from J to K union V must include at least K plus 1 variables, which exceeds the rank of the matrix WJK union V. This result holds regardless of whether V changes its position in the model or not. The authors also consider the scenario where the added edge is removed, and show that this leads to a violation of assumption 3 as well, through a proof by contradiction. The implications of the added edge on the model M, which is obtained by adding the edge to M, are discussed, and it is shown that this added edge does not introduce any new ancestral relations. The analysis then focuses on the minimal bottleneck in the causal graph, examining the relationships between variables in the sets V0, ANM, V, and VC. The sets J and K are defined, and the structural equation of V in M implies that rank WJ union V equals K. The minimal bottleneck must include at least one variable between V and F, V, for each V in K, as well as one variable on the path V0 right pointing arrow ZJ right pointing arrow V in M, implying that the size of the minimal bottleneck is at least K plus 1. This result is generalized to the cases where V equals VK and V equals VKL.